Sit, sir. Sit down.
Yeah, yeah. There are quite a few specific highlights.
So Sandeep, let's discuss the plan with him. So
Okay.
we'll light the lamp, and then who's going to talk after? Okay. You light the lamp? Not more than it's 30 minutes. We plan to 9 o'clock. We plan to start the next session.
Inaugurations which are 10, 15 minutes, ideally.
So then the plan is we light the lamp. He'll talk. Sajal Das will talk, and then we'll talk.
Sajal, you brought him.
Yeah, he's the steering committee. So he'll basically give us the initial.
So this is like every year you are doing this? Yes.
Yeah.
Sajal. Thank you, sir.
So this conference typically, so it happens every year.
And every 4 years?
Every 4 years, going to outside India. So next year it will be in Japan.
So when our team designed a nice logo, before that it was an online.
Namaste, good morning.
Good morning. Suprabhatam, how are you?
Good, sir. Good, sir. Indo-Australia is over population. Hello, I am Murthy. I work at So we have what is called India-Australia Critical Minerals Research Hub. So that is what is this workshop, where about 40 people have come from Australia to discuss about how do we move forward. Because that's becoming very important now for some
Call the volunteers.
material science guys. So I used to go to University of Toronto. There are quite a number of good material science people there. In the center of the city, more or less, your university is also there. So Ryerson is also in the center of the university. Shiva Murthy.
I'm sorry, I don't
No problem. We will meet some other time. Thank you for coming all the way. Next month I am coming there to some.
We'll begin the conference with a traditional lamp lighting ceremony which symbolizes dispelling darkness and ushering in knowledge. I would invite the following esteemed individuals to light the lamp and officially inaugurate the ICDCN 2025 conference. Professor B.S. Murthy, Director of IT Hyderabad, Professor Sandeep Chakraborty on behalf of General Chair and Program Chair, Professor Sajal Das on behalf of Steering Committee, Professor Sukumar Ghosh on behalf of Advisory Committee, and Professor Satya Peri on behalf of Organizing Committee.
set the order.
There's no order. We don't follow any protocols.
Sir, can you
Come.
thank you, sir.
A very good morning. A very good morning to all of you, and welcome to ICDCN 2025, the 26th edition of the conference. So let me start with who's. I am Shondeep from IIT Kharagpur. I am the general co-chair for this conference along with Amos Korman from University of Haifa in Israel. So Amos could not join here due to the current situation in Israel. And along with us we have Satya, who is the general vice chair. And also, unfortunately, I have to represent the TPC chair, who also couldn't come here, but they will be also joining online during the town hall meeting and few other events. Kiara, who is from ICDCN, and Peter is from Augusta University, Georgia. So I have to take a dual role here on behalf of the general chairs as well as the TPC chair. So let me first start with the TPC activities for the conference. So for the main conference, as you already know that we have two different tracks, distributed computing and networking. So under distributed computing this year we got 49 papers, and that is excellent because it is little higher from what we used to have traditionally in ICDCN. And finally we accepted 20 papers, out of which 13 are full paper and 7 are short papers. Under the networking track, there are 28 submitted papers, out of which 12 papers have been accepted and all are full papers. So the authors of the submitted papers, they are from 11 different countries. Obviously the majority is from India and USA, but from other countries like Canada, France, Iran, Italy, New Zealand, Pakistan, Sri Lanka, China and Sweden. The technical program committee, we had 63 TPC members from 16 different countries, and for each paper, they got minimum of 3 reviews, and then there was online discussion across the TPC members to come to a convergence for the papers, for which there was diverse set of reviews, and in that process, although every paper had been submitted as a full paper, some paper have been accepted as a short paper also, finally, a big rounds of thanks to all the TPC members. I have tried to capture their mother tongue here. So if you are a TPC member and if you see that your language is not here, please forgive me. So, regarding the program, we have 6 excellent keynotes this year. So, yesterday during the joint workshop, we had 2 keynotes on 5G and 6G network by Dilip Krishnasamy from CDOT and Kiran Puchi from IIT Hyderabad. Today we have a keynote from Elan Borodin from University of Toronto, Canada on online algorithms and other conceptually simple algorithms. Then tomorrow we have a keynote from Edith Kader from Technion on concurrent data sketches. And finally on 7th January we have a keynote from Nesby Straub from Ohio State University on AI Edge, designing future HD networks and distributed intelligence. So I request all of you to be there during the keynotes. They are going to be the excellent keynotes in ICDCN 2025. Along with the keynotes, we have a panel discussion tomorrow on January 6th on an interesting topic of systems education and research in India. That will be given by Sukumar Ghosh from University of Iowa, UB Desai from IIT Hyderabad, who also the past director from this institute, Arno Pal from MITS Pilani, and Rajdeep Dua, who is from Salesforce from the industry. We have 3 different tutorials. Yesterday we had 1 tutorial on concurrent and LAN data structures. And tomorrow we are going to have 2 more keynotes on compositional network architecture and Open RAN architecture. There is a change in the program. If you see the program, the printed program that has been given to you, originally the 3rd tutorial was on the last day, but we have to shift it. So tomorrow we will be having these 2 tutorials in parallel. Today we will be having these 2 tutorials in parallel. So please attend whichever you want to like. So the technical session, the total papers that we have this year, we have divided into 9 technical sessions who are spanning over the 3 days. And tomorrow at 2 p.m. IST, just after the lunch, we have the best paper candidate session where there are 4 papers. They have been selected as the best paper candidate and based on their reviews, and there will be a jury who will decide the final 2 best paper, one from the networking track, one from the distributed computing track. So this is a motivation for you to complete your lunch early tomorrow and attend the session. Finally, the workshops and other events. So we have 5 workshops this year in ICDCN. Yesterday we had 3 workshops in WDCN, MLBSS and Society. All the workshops were excellent and they have been attended by participants. And on the last day of the conference, that is on January 7, we have 2 more workshops, IWSMN and MLNetSec. We also have the demos and poster sessions today. Around 12 p.m. we have a poster madness session where the poster presenter as well as the doctoral symposium presenter, they will give a 2-minute elevated speech, and then we'll have the poster session outside. So please attend the posters for both posters, demos as well as the doctoral symposium papers. So finally, let me take the role of the organizing chair and let me thank you all the excellent people who are there behind for the past 1 year and made this conference to happen. So I'd like to thank our excellent local organizing chair, MV and Praveen, who are here, I think. The sponsorship chairs, the registration and finance chairs, Arjun. The publication chairs, Shomujit and Franca. So the publication this year was tricky because ACM moved to a new publication model where they are going to publish every paper open access. But in turn, if the institute is not subscribed to the open access model, the authors have to pay an article pricing fee, which is close to $400. And as you know that this is a bit high for our Indian students. Fortunately, and a big thanks to ACM that they have waived all the ACM waiver requests that we have sent to them. So we have got around 14 waiver across the main conference paper as well as the workshop, posters and other events. So thanks to ACM and thanks to our publication chair, Shomujit and Franca, who have taken it up and made the proceedings online. So I hope that all of you have received an email with the link for the proceedings, which is already available in ACM portal. You can see the papers from there. Then thanks to the publicity chairs, Elini, Hirozumi, Mukulika and Fabian for doing the excellent publicity for the conference for the past 1 year. Our workshop chairs, Amitabh and Punnasha, who coordinated all the 5 workshops. The demos and poster chairs, Shantanu and Suketana. Then the doctoral symposium chair, Sogato and Simone. The panel chair, Kishore. The keynote chairs, Valerie and Celine. So we have been able to get 5 excellent keynotes for this edition of ICDCN. And our social media chair, Nisha. So ICDCN has presence in Facebook, Twitter, as well as LinkedIn, and we are regularly publishing all the updates there. If you are not subscribed, please subscribe to the ICDCN page at Facebook, Twitter, and LinkedIn. Hopefully, you will be able to see your photos there soon. The tutorial chairs, John and Mahendran, the web chair, Kotaro, and our excellent webmaster, Vijay. So I remember that for the past 1 year, whenever I sent any updates to Vijay, may it be at 2 a.m. at the midnight, or whatever it may be, within few hours, he updated, he pushed it to the website. Thanks to Vijay for this service. Finally, a big thanks to the steering and advisory committee led by Professor Sajal Das and Professor Sukumar Ghosh, who kept their trust on us, and hopefully we will meet their expectation for this year ICDCN. Thanks to this steering committee and advisory committee members who have helped during the past 1 year with their guidance, with their support and advice whenever we needed that. Finally, a big thanks to IIT Hyderabad and Professor Moti, who is here. This is an excellent infrastructure that we are getting from the conference, the guest house, the auditorium, as well as the excellent kind of services, the food, everything was nice so far. We are going to enjoy it for the next 3 days, and this is a very beautiful campus. I was just walking there for the past 2 days, and it looks excellent, nice architecture, building, and so on. So whenever you get some time, please explore the campus. It is really nice. But well, as a general chair, please also do not skip the session. In between the session or in the afternoon, you can visit the campus. Finally, our thanks to all our technical and financial sponsors to make this conference sustainable and whatever we are there today. So from the technical perspective, we would like to thank ACM for their incorporation approval. Particularly, we have the ACM incorporation from ACM SIGMobile and ACM SIGOps. And again, I thank ACM for helping in the publication process of the conference as well as the workshop papers. Along with that, a thanks to our financial sponsors, ACM SIGAT, for giving us the SIGAT grant. Marvel, who is sponsoring the banquet for the conference. Qualcomm is sponsoring all the student travel grants. So we have around 30 student travel grants that we have been able to support this year from the fund that has been supported by Qualcomm. And first of all, congratulations to all the student grant awardees. You already received an instruction about how to follow the procedure to get the student travel grant. Apart from that, we have support from IARCS, Tihan as the financial sponsor for the conference. Thanks to all the sponsors. So that's all from my side. Enjoy the next 3 days. As I have said, enjoy this beautiful campus, the nice weather here in Hyderabad, but please do not skip the session. Thank you.
Thank you, Professor Sandeep Chakravarti, for sharing the statistics with us and walking through the program. Now, I would like to invite Professor Sajal Das, representing the steering committee, to share a few words with us.
Good morning. Good morning, Suprabhat. Since we are in Telangana right now, Baunara. Thank you very much for coming to ICDCN, the 26th event. I'm representing the steering committee as well as the advisory committee. I'm the steering committee chair, Sajal Das from Missouri University of Science and Technology. And the advisory committee chair, Professor Sukumar Ghosh from University of Iowa is also here. So thanks for IIT Hyderabad for hosting our conference. I visited this campus about 8 or 9 years ago at the invitation of Professor U.B. Uday Desai, who was the director at the time. At that time, I remember clearly, there was only one large academic building hosting most of the engineering departments like electrical engineering, computer science, and mechanical, and most of the things were under construction at the time. But good to see that after so many years I came back, and the campus is so beautiful, with a very good infrastructure, very nice ambience, and all. So thank you very much, the campus, Professor Murthy, the director, for allowing us to host the conference. This conference is truly international. So if you know the history, back in 1999, it started as a small workshop along with another conference, high performance computing in Calcutta, called International Workshop on Distributed Computing. Then in a few years, it moved to a stature to be called as International Conference on Distributed Computing and Networking, because most of the attendees, they thought, this is not a workshop anymore, the quality is so high and all. And since then, the conference has benefited from excellent keynote talks, including Turing awardees over the last few years. And people from all over the world have been taking part in terms of its organization, in terms of contributing as general chair, program chair in different roles, submitting papers and all. So we have come a long way in the last 26 years, and we hope that we should keep the quality very high. So all of you in the audience, if you would like to participate, volunteer, and help to grow the conference, there is a town hall meeting, as Dr. Sandeep Chakraborty mentioned, tomorrow. That is open for everybody. That's why actually collect feedback, statistics, and everything. So Sandeep already has thanked most of the organizing committee members. I'm not going to do that. But the conference cannot be held unless authors submit paper, high quality research papers. So all of you, the students, faculty, researchers coming from academics industry, I think we thank them as much as possible, all the organizers, and we'll have more opportunity to thank the organizers of this conference with different meetings and different events to do that. As I think Dr. Sandeep Chakraborty was mentioning, the main purpose is to network with them. So you listen to the talks, you network with people, you establish collaborations. So please take advantage of that, especially the students and young researchers. When we are students of computer science, don't ask me when, we did not have this opportunity. So you are now volunteering for a very top class conference, you're getting an opportunity, so please take advantage of that. And I'll just make one quick comment on the lighter side. Maybe that's a quick question for you. Why should you attend everybody's birthday? So this is a question, why should you attend everybody's birthday? I'm looking for answers. Why should you attend everybody's birthday? Otherwise, nobody will attend yours. So make sure that you not only present your paper, but listen to others. Otherwise, you know what will happen. Thank you very much.
Thank you, Professor Sajal Das, for his inspiring words. I would like to invite Professor B.S. Murthy, the director of our institute, to share his thoughts.
Welcome to IIT Hyderabad. Already my colleagues have already spoken about the joyful place, IIT Hyderabad, and I'm sure that this particular conference will bring more joy, more networking, as Sajalji mentioned already. I'm a strong believer that collaboration is the key to growth. Without collaborations, there is no growth at all. And we at IIT Hyderabad encourage this more and more. Every year we give funding to our faculty. We call it as collaborative travel grant. So we say just go make friends or strengthen existing friendships. Or you invite your friends so that we can have more and more collaborations happening. And this is, I'm sure, conferences of this nature are opportunities, I would say, to strengthen friendships and make new friendships. And I'm sure I'm not an expert in this particular field. I'm a material scientist and metallurgist. But in every field, collaborations are essential. IIT Hyderabad has been doing its best. Just to tell you, in the last 1 year alone, if I look at the total amount of research funding that we have got, almost 50% of the funding has come through collaborations. So that's the power of collaborations, and we would like to do more and more of that. And there are possibilities of what is called joint supervised PhD programs we have with a number of universities already. And I would like all of you to look at those opportunities. How do we, because PhD students to a large extent is our strength, and that is through them is what we do all our research. I have supervised about 55 PhD students in my life so far, so I know this very well. So they are the main people who do research where we get involved, and in every PhD, through them we learn a lot. And this, if we can have this as a jointly supervised PhDs, where there is a value addition to the PhD thesis of the student by both the supervisors coming from two different universities, two different cultures sometimes, and two different institutions. And at the same time, the faculty on both sides also have something to learn from each other and grow together. And I think growth should always be an inclusive growth is what I believe in. And when we work together, it definitely becomes an inclusive growth. So I wish this conference all the best. And I've heard that possibly first time we are doing this in Hyderabad, IIT Hyderabad? Yes, IIT Hyderabad first time, good. Very good. And as my friends pointed out, there's a beautiful campus. Please go around and enjoy it. And of course, after the lectures, as my Sandeep already pointed out, I can tell you this. I have spent about 2 years in Japan. And Japan, typically there is a conference going on. From morning when the conference starts until the evening 5 o'clock or so, when the conference ends, everybody is in the conference. Okay, and that's something which in India I don't observe it often, So I urge all of you, there's a lot to learn from these lectures, and they have done a lot of screening and brought out the best people for all of you. So please do attend, and there's a lot to learn from that. And then of course, whole of evening is there. Yesterday night, 9 o'clock, with about 40 Australian delegates, I was roaming in the campus from 9 to 11. I was taking them all around the campus. If you are interested, I can do it today night for all of you to show our campus and tell how beautiful it is. One of the best campuses I can say in India, and at the same time, one of possibly the fastest growing IITs in India. A lot of innovations are happening to the extent that we say IITH is not Indian Institute of Technology, Hyderabad for us. We say it is inventing and innovating in technology for humanity. So that is how IITH stands for all of us who are sitting in IIT, and we want to do that, and we want to ensure that innovations bring a big change, big transformation in the country, and make India what our Prime Minister's dream is for those who are coming from outside. We call it as Atmanirbhar Bharat. Atmanirbhar Bharat, for those who possibly do not understand Sanskrit, is a country which is a developed country. India is still being called developing country. Okay, we want to remove that in form there and call it as a developed country, and that is something which we feel together we can achieve. I keep telling that last month, 1 week I was in Melbourne. So for me, a developed country is one where not only excellent research happens, but also we develop products which are sold everywhere. If I go to Melbourne, I shop in Melbourne and buy a product, and I open the packet, that it should be written made in India. So for me, that is a day where I can call as we are a developed country. And I think all stars sitting here, PhD students here, and undergraduate students who are being involved in this kind of conferences are the ones who should make that happen, and I'm sure together we can make that happen. Thank you very much, friends. All the best to all of you.
For encouraging us and sharing his wishes for ICDCN 2025. Now I would like to invite Professor Sukumar Ghosh sir to start the keynote session.
Good morning, and it's my pleasure to introduce the first keynote speaker of today, Professor Alan Borodin. Professor Alan Borodin is a university professor at the University of Toronto Computer Science Department. He is a world leader in mathematical foundations of computer science, and his research has impact in virtually every area of theoretical computer science. Professor Borodin joined the University of Toronto in 1969 and served as a departmental chair between 1980 and 85. He was a visiting faculty at Cornell University, ETH Zurich, University of Nice, Hebrew University, and the Weizmann Institute. He is a fellow of the Royal Society of Canada. He is an ACM fellow. He is a past recipient or past winner of the CRM Field Spins Prize back in 2008. And he is a member of the Order of Canada. Today, Professor Borodin will be speaking on online algorithms and other conceptually simple algorithms. Please welcome Professor Borodin.
Average set of so I think it's, as the director said, collaboration. I'm anxious to kind of make more connections. When I was creating this talk, after a while, I realized that online algorithms are not unfamiliar to this community, both people in networks and in distributed computing. So I changed it a little bit, and we'll see how it goes. I haven't seen the campus yet. I guess it's a great thing, but maybe wait until I finish talking before you go to see the rest of the campus. Okay, so let me make a first attempt to say that was relevant because you already have papers in the conference that have that feature online algorithms. And last year at this conference, there was a paper, and Lata will be speaking about it tomorrow, a follow-up paper in this year's conference about renting servers in the cloud. And without reading the whole thing, there's some words that I want to point out, and I'll point out again, that this is about online computation, things arriving online. There's a natural algorithm for the problem, first fit like in bin packing, greedily assigns jobs, word is greedily, and the algorithm is conceptually simple, but yet algorithms often that are conceptually simple are not so simple to analyze, which is one of the things why I find them fascinating. Okay, so this year there's a follow-up conference about multi-parameter jobs in the cloud, and again the words natural comes up, here greedy algorithm comes up, and the comment that greedy and might say other conceptually simple algorithms perform well in practice. So to beat this to death, there's words, greedy algorithm, natural, conceptually simple, notoriously difficult to analyze, greedy performs better. You see that in many papers, those comments. Okay? So, good. With that introduction, why study conceptually simple algorithms and what are they? Okay? Well, greedy algorithms, I think most people would say, usually are conceptually simple. We teach them in undergraduate courses, so I guess they must be simple. Online algorithms really are kind of within the same vogue as greedy algorithms, and I'll say what the connection is between them. But I would suggest that if you were really faced with, say, some combinatorial optimization problem, the first thing you might try is a greedy algorithm or a local search algorithm. Those are the things that come to my mind. It may not be a great algorithm, but you'll get something running. Okay? And other conceptually simple things, well, some, not all, but some divide and conquer. Some are very, not simple. Divide and conquer dynamic programming algorithms can also be considered conceptually simple, and some very simple IP/LP rounding algorithms. These are the kind of things you try first, and often they wind up, if not being what you're going to want, if not being the final product, or they're an initial product, they become a benchmark that you can use, and you get a good insight into just how difficult the problem might be. Okay, so the question is, to what extent can we make these algorithmic paradigms precise? We, again, teach them in undergraduate courses, but we never define them. I don't know if you know of an undergraduate textbook that actually gives you a definition, a greedy algorithm, in a formal, precise way. Okay. In particular, you want to get a definition that not only captures what's intuitively think it means, and captures most of the algorithms or many algorithms that we have in mind for that paradigm, but we can actually analyze these algorithms and prove limitations. Okay. Good. Okay. So, I'm not watching time. Will somebody flag me down, right? And all that will happen is I'll start speaking faster. Okay. Good. So, but what you give me maybe a 10 or 15-minute warning or something, or I don't know. Well, do I have an hour or not?
Have an hour, yes.
An hour. Okay, good. Because we're starting a little late, so I didn't want to get cheated. Okay. All right, good. So I guess everybody would say, well, we kind of know what an online algorithm is, and perhaps we do. But I'm not even sure we even know what an online problem is. And so here's one very generous framework for an online algorithm, but not for all online algorithms. Again, and it actually also works for greedy algorithms, but I'll say why. But a framework that's aimed at combinatorial optimization, pretty much. And the idea is that there's a set of requests, things and they come in, they're going to come in one at a time, and there's an answer set. For each request, you have to give an answer. Okay, and the infinity for a minimization problem means that certain solutions are not acceptable. Okay, but you want to say what the cost function is for every answer you've given for every request. That's a pretty general framework. And there's an analogous framework for maximization problems. And the understanding is the adversary presents these requests in a sequence, and an online algorithm must respond to each request with an answer before the next request is presented. Okay, and the cost is the final cost. Okay, so, but to make it really precise, if you really want to prove a bound, you have to say, well, what is, how do you represent each input and how do in each answer? Okay, so you have to talk about actual representations. And of course, you'd like natural representations, but some problems admit many natural representations. If you have a graph problem, an input item could be an edge, or it could be a vertex, and a vertex could be a list of adjacency lists, or there's different possibilities. Okay, it could also be presented in some graph theoretic framework. Okay, so good. And now, as I say, it's aimed to model optimization problems, combinatorial problems, navigation problems, like if you have some sort of a map with obstacles and you're trying to find your way around it, or what's a very familiar classical online problem is a navigation problem. It's the line search problem, or a generalization called the cow pasture problem. You have a point in two-dimensional space and arcs going off, lines going through, all going through that origin, and there's a hidden object on one of the arcs, and you have to find it. So you go a certain number of steps, and if you didn't find it, you go back and try another thing. And, okay, so very typical, but that's a navigation problem. Games that we play on our computers and waste a lot of time. The thing that's I'm addicted to is Wordle. I don't know if anybody's played Wordle, but there's a hidden word that you're supposed to find, and you put in a candidate, and it tells you what's right and what's wrong and where they go, and afterwards, if you want, we can play the game together. But in these problems, these navigation and these game problems, it's the algorithm that's making the request say, oh, here's what I think it is, and it's the adversary that's answering it in some sense. Okay, especially in the navigation problems. You say, I'm going to go 10 spaces in this direction. Did I hit an object? You know, did I hit something? Didn't hit something? Did I find the object I'm looking for? Okay, but I'm not going to talk about that. But I'm saying this type of framework is quite general, and online algorithms include navigation problems. Okay, so here's some classic problems that are studied in online computation, and they all fit within the request-answer framework. I'm not going to define them all. I'm just assuming that most people have heard of the terms. I think everybody. Some of these algorithms, some of these problems are intrinsically online, like the paging problem, like list accessing, or in many data structure problems, ski rental as a buy or rent problem. Other problems, the rest of them could be viewed as offline problems or online problems. And again, a little connection to the conference called processing and networks is a familiar topic in online algorithms. Are these problems more or less known to everybody, or not? Or should I mention a few of them? Is there any one of these problems that looks strange? No? Okay, good. Nobody ever says anything, so, but I thought I should ask anyway. Good. Okay, I'm going to talk a lot about, if I can get this to work, where's the, well, oh, this map. I'm going to talk a lot about interval selection later, okay? Because I want to pick out one problem in particular, but, good, okay. Besides those various problems that you've seen in any, say, on most undergraduate textbooks, there are two very abstract frameworks that still fit within the request-answer framework. And those are the so-called case server problem, which briefly is that case servers are in a given metric space, and a request is a point in the metric space, and you must move one of the servers to it. The other problem is metrical task systems, where let me just talk about the case server problem for a second. The case server problem is a famous problem in the online world, and I want to say that's the importance of formulating interesting problems. It's a very abstract problem. Nobody solves any case server problem in practice, okay? But it's such an interesting problem. A conjecture was made that you can always get a good approximation, a constant approximation, in effect, for this problem, independent of the length of the sequence, independent of the size of the metric space. It was a bold conjecture, and yet it turned out to be almost correct. The conjecture was that for every k, the ratio is k. Okay, but one can't say enough about the importance of a good model, a good question, a good conjecture. That conjecture has led to interesting things that have influenced things well beyond online algorithms. In particular, there's a result by Bartel, which is a new embedding method of an arbitrary metric space into a particular type of a metric space, and it has been used outside of the online algorithms community. So my feeling is that P.T. Barnum used to say the only bad publicity is no publicity. The only bad conjecture is no conjecture. And I think these conjectures really lead us to thinking about things, and all sorts of problems have come up in metric space problems, and I think there's been tremendous influence by that very abstract problem. The metrical test system also ties into it online learning. It's also had an impact, even though it's extremely abstract. Okay, good. So then I'm giving up motivating. If I haven't motivated enough, I'm not gonna succeed. Okay, but I do believe that say distributed. I don't work in this community. I wrote one paper. I was involved in one paper maybe 50 years ago. I can't even remember what it was, but I've always followed it because we have three excellent people in distributed computing at the University of Toronto, so I hear talks, but I really am not at all in the community. But again, it's clear that in this community you have models, and like the congest model for distributed computing, the SINR model for wireless networks and things like that, which people use very productively. And okay, so now let's get on with an online model and what's called competitive analysis. Okay, good. So here is the template for an online algorithm. Okay, and it seems pretty obvious, but I want to point some things out about it. Okay, so what happens is you have an instance which is a sequence of, if you want to say, requests or items coming in. And while you still have things to do, while you haven't exhausted all of the requests, you have to answer them one at a time. Okay? And you make an irrevocable decision about for each element based upon everything you've seen up to date and all the decisions you made. Okay? The template is, I said, is shamelessly copied from a new text I'm writing with Dennis Pankratoff at Concordia University, and it's hopefully completed by summer 2025, and I've said that for the last 3 or 4 summers. So, I don't know, 3 or 4 years. But anyway, the decision just means that the algorithm can store everything it wants. There's no memory constraints. There's no time constraints on how long it takes you to make a decision. Okay? And when I say the while statement, we have another template which would have a for statement when n is known. You would say for I equals 1 to n. But while just means just keep on going until somehow the adversary says, I've had enough. And it says, you're finished, and here, let's see what you did. Okay. I was going to talk originally more about some other conceptually simple algorithms that we can model formally, and one is called priority algorithms, and that's a model for greedy algorithms. And I'll just briefly mention that, just so that I'm a little bit honest to the title. And the way to think about first a fixed order priority algorithm is that you impose an ordering on the input items. Now the algorithm does that, rather than an adversary who's presenting the sequence. Okay? The adversary presents a set of items, but now you get a chance to order them. Now, of course, you don't want to order them, you don't want to say, I'll order them by the best ordering. So you have to have some legitimate rules about what you mean by some sort of a reasonable ordering. And that's not going to be based on time and space. That's going to be based, information theoretically, on sort of something that's very local. You would, it's more general than that, but what you would do is just say for each input item, in whatever representation you have, give it a real number, say. Have a mapping from each input item to a real number, then sort by those real numbers. And if you think about it, a lot of greedy algorithms and online algorithms work just that way. Not online, greedy algorithms work that way. So you have a fixed ordering, and now after you have that fixed ordering, you'd like an online algorithm. Okay, you got the choice, you got some flexibility in how you order things, and now you proceed like an online algorithm. A more generous type of greedy algorithm is a priority algorithm, is an adaptive priority algorithm, where after you've seen the first items, you think again about what the ordering should be, in particular what the next item should be. And you, based upon everything you've done to date, you now create, you say, oh, give me the next item according to this criteria. And that's, but that gives a lot of generality, because you not only you know something about the current item, you know all the previous items you've seen. So therefore, you know certain things can't be there, and therefore it gives you a lot of power. And I want to say that greedy. This is a generalization of greedy, as I think most of us think about greedy, in the sense that you don't have to be greedy. greediness is a property of the decision you're making. And sometimes you have to, for each problem, say what I mean by that, but it's sort of a live for today. Forget that there's going to be more inputs. Do what is optimal right at this moment. Okay. So that's the framework. And many of the things I say about online algorithms will, not all, but will apply to priority algorithms. Okay, so we can, the same types of questions and issues, and some types of the results are like that. So is that framework more or less correct, reasonable and understandable? Okay. Again, I don't ever get, nobody ever says no, so go on. But it makes me feel better. Okay, good. So then you have something which is the analog of approximation ratio. I'll just throw the definition up there, but I think if you think approximation ratio, that's what it is. And we usually assume it's an asymptotic approximation. We're really only interested in as the optimal is growing, what the ratio would be, the ratio of how well the algorithm did to how well an opt could have done on that input, an all-powerful optimal. You don't care anything, no rules for the optimum. The optimum doesn't have to be, and by the way, even in the online framework and the priority framework, the decisions you make don't even have to be computable, so they're well-defined decisions. It's just completely information theoretic. Okay, so sometimes people talk about the strict competitive ratio, where there's no little o of opt term at the end. Okay, all right. Okay, and then you can talk about the competitive ratio for a particular problem by considering the ratio over all algorithms for that problem. What's the best ratio for any algorithm? Okay, and then conversely, what's negative? What's the provable that you can't do certain things? Okay, so well-formed, these are all well-formed problems. Randomization, of course, always adds a great deal of power. But it also adds a lot of additional questions you have to ask. So the only thing in an online algorithm that's randomized is the decision. Okay, and you can have a randomized decision, and then the algorithm, of course, has what the algorithm does is a random variable, and you have an expectation for it. So you just change the definition to include the expectation. Notice that I didn't put the expectation in opt, because generally speaking, and I'll say why, opt is not going to be a random variable. And why is that? Well, the randomized algorithms say what is the nature of the adversary. And what I'm assuming throughout, what most of the people assume in online algorithms and what they assume in offline algorithms is what's called an oblivious adversary. Terrible terminology, but whatever. An oblivious adversary just sees your algorithm and decides, okay, here's the nemesis set. Okay, and then it loses control. Okay, an adaptive adversary watches what you're doing in some sense, sees the decisions you're making, and then figures out what to ask you next. Okay, and those come in two varieties. Those where the algorithm, the adversary, even though it's creating the request, still has to answer it right on the spot, just like the online did. And then the other thing is that no, it doesn't have to do that. It waits to the end to give the complete answer, okay? And but then there has to be an expectation in opt. There's the ratio of the expectation. It's the ratio of the two expectations, not the expectation of the ratio. Okay. Good. And then what's important here is that once you get into adaptive adversary, the adaptive offline adversary, what ratios you can get against an adaptive offline adversary is the same as a deterministic adversary. It doesn't, the randomization against an adaptive offline doesn't get any power over deterministic. For adaptive online, there can be some benefit, but due to the way most of the algorithms, the arguments work, there's often no benefit. Okay, but so in the online community, people usually, and offline for sure, are just thinking oblivious adversary. But as I understand it, maybe in the distributed computation, maybe the adaptive adversary is more reasonable. So it might be interesting to keep in mind that it may, I've never worked it out, but you can think about it. If you have an adaptive adversary, is it really what is the nature of that adversary and how much you're gaining by randomization. Okay, good. Yeah, so that's the ratio that it could square the ratio, so, but often it doesn't do that. Okay, and as I say, we usually assume oblivious adversaries. That's my assumption. If I talk about randomization, that's my assumption. Okay, there's also a little distinction you have to make. Some online algorithms are in the mode of what I would call real-time algorithms, like used in scheduling theory. That the next item is not just completely arbitrary. It comes at a particular real time. And the items, the I plus I first item comes at a time after, no sooner than the ith item. You can have many things occurring at the same time, but they have to occur according to this clock, according to the actual real time it appears. In the online community, you don't really, some people do consider real time as part of that philosophy, but if I say an online algorithm, I make no assumption about a clock. I make no assumption about the order in which things are coming in. Okay. And then in real time, you have to distinguish between clairvoyant and non-clairvoyant. When the item comes in, do you know everything about it, or do you only find out about it when it terminates? And the talk that Lata has given is about a clairvoyant real-time algorithm, but still online. Okay. What's the good and the bad of the online framework? Okay. The good is often you get reasonable bounds. They're not tight bounds, but often you get reasonable good bounds, and in many cases, very natural algorithms provide decent, put everything in quotes, positive results theoretically, and often perform decently, pretty well in practice. So it seems to be, even in spite of its generality, we tend to create algorithms which are conceptually simple and useful. And I want to point out that the absence of this memory and time considerations makes the analysis much more general, and it gets around our inability to prove results, specific results for combinatorial, say, optimization problems, say, within the NP framework, where you actually want to say this can't be done in time n log n or something like that. We don't know how to do that. We do not know how to prove results for an arbitrary algorithm saying it can't be done in a particular time or a particular space. That's a sad fact. A lot of progress in complexity theory, a lot of good intuitions, but no results, negative results of any general nature. Okay. This gets around that because it's all information theoretic. So we can say, no, this algorithm, online algorithms can't do this, okay, without worrying about it. Okay, what's the bad of it? The bad of it is just like the bad of any sort of worst case analysis. Okay, this is worst case analysis as it was first articulated. We're doing this over all possible input sequences, but not all possible sequences exist in the real world. Okay, so we have to get around that, and often the analysis doesn't really distinguish even between algorithms, not much less between theory and practice. Okay, so we want to get around that, and this absence, this great possibility about the absence of complexity assumptions means that sometimes you wind up going and creating rather bizarre algorithms that are still online, but loses the intuition behind the whole raison d'etre for wanting simple algorithms. Slater and Tarjan, though, they weren't the first to study online algorithms and study competitive ratios. There's nobody, and even they didn't call it that. But they were very explicit in saying, this is a good way to analyze things, much better than making average case assumptions. Well, it turns out they were right for the list accessing problem, moved to the front, turns out to be great theoretically and great in practice. But it didn't tell you anything about paging. LRU, least recently used, is a great algorithm in practice and in theory. FIFO, not so much, but the theory doesn't tell you there's any difference. Okay? The basic theory. Okay, so how are we going to get around this? How are we going to overcome these limitations? Well, we're going to overtake it in two ways. I think in general, and maybe there's more, but I think these are the two. You weaken the adversary in some way. And the most reasonable way to weaken the adversary is to say that you have some stochastic or distributional assumptions about the data. Or you limit the data in certain ways. I only say, oh no, I'm only interested in graphs that have a certain property, or degree 3 or something. You do that. Or sometimes you need to introduce the idea of locality of reference, like in paging. Okay? In some sense, even randomized algorithms against an oblivious adversary limits the adversary. The adversary just knows the algorithm, just knows the algorithm, doesn't know what you're going to do for the algorithms. It knows in some randomized sense what you're going to do, but it doesn't know precisely what you're going to do. So it's weakening the adversary. Okay. Or you can strengthen the model. And the one very popular way to strengthen the algorithm is to give it recourse, to allow it to change. Before now, everything I was saying before for online and priority algorithms was you make an irrevocable decision. Now you don't. Okay? Now you have some way to change previous decisions, and you have to say at what cost or how, in what way. You can't just say change it arbitrarily, otherwise you're back to an offline algorithm. Okay. And what's now, well, you can delay decisions for some while. In scheduling, that happens all the time. There's no, in real-time algorithms, there's no compulsion to make an immediate decision. You can wait. But of course, by waiting, you're hurting the objective function maybe. So, okay. So it's built in intrinsically into it. Or the thing that's popular now is predictions, allowing the algorithm to make predictions. That is, and the reason for that is because people have, it's a very nice approach, but the reason that is very popular is because it's called online algorithms with machine learning. And now you can get into all the AI conferences. So the world is expanded. Okay, but it's actually a very nice perspective. So of course, these ideas are all complementary. You can, talk about stochastic optimization, stochastic inputs for models where you've added generality to the model, and of course the results become quite interesting theoretically, but not often very non-trivial. And if I have time, I want to present one result about interval selection, where we're going to look at a very limited form of recourse where you can, with some maximization problem, where things that you accepted before you can get rid of in favor of better things. Okay? And then we're going to do that in a model called the random order model, and I'm going to discuss that shortly. And that, I think, is probably one thing that I do want to get across, and I think maybe people are familiar with that concept, but I want to say just how important I think that stochastic approach is. Okay, so did I get to it? Yeah, good. The random order model. So the random order arrival model, or some people say ROM, random order model, is that the adversary again presents, gives you a nemesis set of input items, but now nature takes over and scrambles it and presents the items in a uniformly random way. Okay. So, so this again is going to lead to stochastic results, because that's now, again, your performance will depend upon exactly which permutation of the items you got. Okay, fine. So, but there's still online algorithms. The online algorithm has no control over the sequence. Just nature took over. The adversary lost control, but the online algorithm didn't gain control, like in the greedy algorithm setting. Okay. So it's a great input model. It doesn't make sense in the greedy sense, the priority sense, because there you've already given an order, so then why square the order? It doesn't kind of make too much sense. Although you can compare how good, say, is your power when you can order things versus when nature orders them randomly. Okay, so it's very natural, because it really, and it much better represents reality. We may know the kinds of things we expect in a given day for requests, but the order they come in is often unknown. And I think that would be said about distributed computation. They can come in quite random orders in some applications. You tend to do experiments by getting synthetic data and doing some randomization to it like this. And it often leads to much better results than for adversarial sequences. And it's quite often closer to reality when you actually do experiments or look at real data. Okay, so the random order model also has this great property. There's a typo there. I knew I'd have at least one typo. Okay, hypothesizing this lineage. Okay, you often hypothesize a distribution and say that each input item is drawn independently from that distribution, independently and identically. So that's called IID. If each item is coming independent but could come into a different distribution, it's just ID. And the result is that random order, if you have an algorithm that has a competitive ratio rho with respect to the random order input model, then it will have this at least the same competitive ratio in the IID model. This is a very general result, and it's for an unknown. You don't even have to know what the distribution is. You'll do as well for any distribution. You're going to do as well as you did for the random order model. And now this result, as far as I know, was implicit in a result by Claire Kenyon in 1996 for bin packing, where she was analyzing best fit and saying why it can theoretically be shown to be better than first fit by saying it has a better ratio, provably better ratio. Okay, but it explicitly stated in the context of online bipartite matching by Carende et al., and where they actually say it. And the proof is one paragraph. So one paragraph proof, and yet such an important, I think, result. And often one proves negative results about random order things by proving the negative result about a particular distribution. Okay, good. All right, good. I want to talk about the classic secretary problem. So the random order model, though, has been around for a long time. It is the model, when people talk about the classic secretary problem, that is the random order model. The classic secretary problem has all these different names. Sultan's marriage problem, it's a folklore problem, became popularized in a 1960 Scientific American article. And the idea is candidates come in one at a time, secretaries, candidates, prospective queens, whatever. And each time the king or the algorithm looks at each candidate who come in with some qualities, some value. And you either say, I take this one, or you discard it. I guess royalty, maybe they lose their life or something, but whatever. You just say, you don't look at it again. And then eventually you pick one, and that's it. The game ends. You can't do anything adversarial. If you have adversarial order, you get terrible results that depend upon what the actual values are. But independent of the values, you get an absolute constant if you assume random order. So random order has a tremendous amount of power, and it's a very natural problem. If you actually, then it's applied to auctions, and sometimes items are buyers interested in a product and so on. And then you have a lot of stochastic information about it, and these leads to problems which are called profit inequalities and profit secretary problems. And very, very important topic, very much used in the auction literature. Okay, so I said that's the actual ratio you would get for deterministic. It's trivial to get L over which way? Okay, let's say U over L. You get trivially U over L deterministically just because you can't do worse than choosing the lowest value from choosing the highest value. With randomization, you can get log of that. And that's the best you can get in adversarial order. But with random order, you get an absolute constant. Okay? So it's a classic example where classic is spelled, where a deterministic algorithm is arbitrarily better than the best randomized algorithm. Okay? So that, to me, raises a very interesting question. And we have many examples where a deterministic algorithm in the random order model is provably better, or at least as good, but often provably better and sometimes much better than any randomized algorithm with respect to adversarial order. Now, what about the other way around? Is there any application where, especially a natural online problem, where a randomized online algorithm in adversarial order is better than the competitive ratio for any deterministic online algorithm in random order? It seems to me a very obvious question that hasn't been asked before, and I don't know how to answer it. Okay, because I cannot think of one. I don't even have a candidate for, where we suspect it's happening. But I have no evidence that of the absence of this. Okay, so I want to talk about all these things in the context of one specific problem. How am I doing, and what do I have left here? 15, yeah, this is where I said I'm going to talk faster. But in India, people talk fast, so, I feel I'm at a tremendous disadvantage, so I'm going to put you at the same disadvantage and speak fast too. Okay, so interval selection, a very natural model for this is an interval comes in as a pair. I'm not talking about it in the graph theoretic sense of the interval graph. Interval comes in as a pair, a starting time and a finishing time. And I'll let the next one could actually start when the other one finished, but that's not important. Okay? And what you want to do is, and they may have weights, each interval may have a weight. And you want, and interval scheduling has tremendous amounts of applications. And you want to, in the weighted case, a feasible solution, you can't have any intersection. And you want to maximize the value, the sum of the values of the intervals in a feasible solution. And if it's unweighted, it's just the number in a feasible solution. Okay. Except for some very limited cases, you put some constraints on the types of intervals you have. You can't get constant determinists or even constant randomized competitive ratios in the traditional online model. Okay, where decisions are irreversible. Okay, so we want to talk about the problem with revocable acceptances, and then even with revocable acceptances in random order. Okay. Okay, so again, no temporal assumptions. If you assumed that things were coming in temporal order, if you could assume that the starting time for the next one is at least after the starting time or at the same time after the previous one, then you could do something without revoking. Okay, so I want to consider, and then of course you're interested in a deterministic or randomized algorithms, and if you have randomization, you're always interested in how much randomization. Okay, and do we assume any external advice? Do we have this ML prediction error versus performance? And that was first introduced in an article by Likorsky and Vasilevsky. Okay, so a lot of different considerations. So it's an old problem, been studied for many years and still isn't what we learned about it. Okay, and then the recourse is that I'm going to allow you to revoke previous accepted items, and then I'm going to say we're going to, and I'm going to also interested in adversarial order and in random order. When intervals come in random order and come in adversarial order. Okay, and as I said, these things. There's other considerations of what other stochastic models you could have. And I'm also interested in this idea of how much memory is required to get good at competitive ratios, but we can't say too much about that. It's not part of the initial philosophy, but it's a very interesting question. And so, of course, this memory is the focus of streaming algorithms. Okay, so there's a connection between interval selection and disjoint paths on a line. So, an online network. You can talk about disjoint paths or call processing on any network, but in particular on a line network, you have a call which starts here and ends at some node and ends at another node. And if it's a line network, you can see it sort of looks like interval scheduling, interval selection. But there is a difference, because in call processing, you know the graph in advance. Okay, and you know, as soon as you know the size of the graph, you know there's a limited number of different types of calls you can have. Whereas in interval selection, you can have, uncountably many different intervals, okay, depending where they start and end, okay? And you don't know anything, So in call processing, you tend to get ratios if they're not constant, depending upon the size of the network. In this adversarial, competitive world, you think in terms of the length of the input, if you can't get a constant, or some other parameter, okay? And then there's proportional weights, which is a special type, where the weight of the call is the path length of the call, and in the interval selection thing, it's the Euclidean length of the interval, or something like that, okay? So that's a natural assumption that the longer the call, the more you should charge for it, or something, or the more the profit, okay? Intuitively, interval selection seems a little harder, but generally speaking, results line up. There is a order of log of n, capital N, the size of the network, for unweighted call control on the line, and that's optimal. Okay? And there's very precise 2 plus square root of 5 for proportional weighted call control. We can move over the proportional one to the interval selection, but when I restate the approximation for call control, it becomes omega of little n, the length of the sequence. And that's as bad as can be. You know, I mean, you get a bound of n over 2 and n, this is as bad as can be. So you really don't get anything theoretically in this adversarial model, even with revoking. Okay. You can parameterize problems and you say, well, you know, I know the length of the longest one versus the shortest one, or you can talk about how many different lengths there are. A very special case that's studied is when there's only one length. Okay, but if there is k lengths, then with Chris, my student who just graduated, we can prove that for deterministic and so-called memberless randomized algorithms, 2k is the optimal competitive ratio if there's only k distinct intervals. Okay, you can prove that in the unweighted case, you can get a constant thing for randomized algorithms with revoking. Okay, and without revoking, even with randomization, you can't get anything. So you need both revoking and randomization. Okay. Now, so what we could prove in a more recent result is that we have a very simple, the algorithm, I don't, okay, I'll even mention it. The algorithm that gets 2k for adversarial inputs actually achieves a constant ratio in the random water model. Okay, so, and what I like about this result is that, first of all, it's interesting technically. It introduces some new ideas. It introduces a new type of charging argument. It also uses a result that I've not seen used outside of one paper, and the paper is by Neil Young, and it uses something called Wall's inequality versus Wall's equality. Wall's equality is a very famous result in probability stochastic in statistics. The result says if you have a sequence of random variables, they don't have to be independent. And if you have a bound on the expectation of each of these things, and you know that they can't be too bad, then the sum of the expectations is bounded. Okay? And it holds for minimization and maximization types of things. Okay, so I don't know if anybody else has seen that. I've never seen it any other place, and we need that. Okay, it's the random water study many things. I re-asked that question again, but another way of phrasing this question: is there something that can be done by a randomized algorithm that can't be done as well by a deterministic algorithm in the random water model? Another way of thinking about that is, can I extract randomness from the input sequence? And I have to extract it in an online manner. Okay. Now I'm really getting tight, right? Where are we?
Yeah, you can take 6-7 minutes.
10?
6 to 7.
6 to 7. Did I hear 10? No. Okay. 6 to 7. All right. So what we, and we show in the same paper a certain algorithm for when you have 1 and 2 lengths, for even with arbitrary weights, how you can extract randomness from the random order sequence, okay? And I won't have time. But let me say that a lot of these issues that I'm talking about go well beyond interval selection, which is a very nice problem to study because of its historical significance, because we know so much about it, okay? And one of the things I've been looking at with another, my graduate students, Ben Cookson, we're considering kind of conditions when a fixed order priority algorithm without revoking can be simulated by an online algorithm with revoking. And in hindsight, we can show this is why the algorithm that we sort of all know from undergraduate textbooks for unweighted interval selection, where you just sort by the finishing time, but that's a priority algorithm, you have to sort first, can be achieved with online with revoking. Okay, and we can sort of explain that in a more general context and apply that to some other limited examples. Okay, so that is another general aspect that I've been looking at, is how, generally speaking, how non-online algorithms sometimes can be converted into certain types of online algorithms. Okay, and I'm just going to flash through the proof. Unfortunately, the proof is, I've sketched the proof. It's about 8 or 9 slides here, but the actual proof is technical. Okay, but I'll say with the algorithm is the most obvious greedy algorithm you can think of, and that is okay. It's unweighted, right? So an interval comes in. Well, if the only time I want to reject something is if this interval is small compared to the thing that's sort of fitting in. Why would I want to keep this big thing when this little thing will get me just as much value? And that's it. That's what you do. Okay? You can't think of something simpler than that, or if you can't, let me know. And that algorithm gets to 2K when this K distinct intervals, and it gets this constant. Okay, when you have random order, and it's a little technical. You have a charging order that's changing all the time, given by the random order, and you're redefining the charging as the execution is going on. That's somewhat unusual type of an argument. And there's 2 types of charges, direct and transfer charging, because you're revoking. And you could say, well, there's never too many things by direct charging that can be charged to the same online algorithm. The online solution, you always map, say in this case, mapping from an optimal solution to an online solution. And so then what you have to do is estimate the expectation on the transfer charging. And that's where the technical work comes in, and you need the outer shell of the argument is to use this Waltz inequality, which you can then plug in like that, because it's the expectation of these individual charges that you're making, okay, that's the outer solution. But the inner solution is how do you actually estimate the transfer charging, the expectation of the transfer charging, and that's a pain in the neck. Okay, it requires a lot of tedious, just computational, probability estimates, and it depends about you have to start off with a sort of a very typical solution, a typical instance where you have 2 different interval lengths. So if you only have 1 interval length, there can't be any nesting. When you have 2, there can be a limited amount of nesting. The more intervals, the more nesting. Okay, and then the transfer charging has to be passed on. Okay, and what is a typical solution? What does an instance in this thing look like? It looks like this. A lot of these big things, something big or small to the left and right of it that intersects, and things underneath. It's sort of like that. And you analyze that. And that's already technical computation. And then you have to say, okay, for arbitrary instances with 2 instances, how do they piece together? Okay, and they piece together, but this is the calculation, somewhat of the calculation for just the basic case. And then you piece them together, and you find out, and this is the piecing together, you find out the expectation is 0.5. And so you get the 2 plus 0.5. Okay, what I think it's an interesting result. I'll just give you a hint of how we do this extraction of a random bit. We can do this for other problems like knapsack problems. In the phone algorithm, this is for weighted interval selection with a single length. We can extend that to many lengths, but for one length, an interval, you can think of an interval starting at some starting point and ending point, where the starting point, the nearest left point is an even integer or it's an odd integer. So you have two types of intervals, okay? And what you want to do is just say, oh, you know, depending on which type came first, that'll be a random bit. Okay? Now, if all the items were distinct, if you had some way to say that, then that would be a probability half. But if the items are not distinct, then there is some correlations, and what we can prove is that you get a bias coin. It's a 1/3 bias, meaning that the probability between 1/3 and 2/3, what's happening when you look at this, whether you get type 1 before type 2 or type 2 before type 1. And it turns out that the case that you think might be the good case, where you have the exact same number of even and odd intervals, turns out to be the bad case. Anyway, that's another little piece of analysis. And I think that's an interesting phenomenon, is when can we extract randomness from the sequence. And as I said, it becomes a 1/3 bit, what do I still have to say? How general is this random extraction idea? That's a very good question, I don't know. But we think we can make it for a number of other problems. We can't get past, by the way, we can't get past 2 intervals for the interval selection problem, but various things go on that makes it not so easy, because you got to extract the things fast enough. All sorts of other questions. How important is to know the length of the sequence versus not knowing it? And that turns out in many problems to be very important. If you know the length of the sequence, like in the secretary problem, then you can use some prefix of the sequence to just sample the sequence. And then I gain information about the distribution by doing that. If you don't know that, you can't use that idea, okay? And so they have results like that. Our paper doesn't require you to know the result. And if you don't know N, you can prove some things in the our paper about that you can't do things. If you don't have, they look at random order but no revoking. Okay? So you need these properties together. I'm interested in the role of memory. I know the idea of a memoryless algorithm is that the only thing you're storing from any point in time is the current solution, basically. And if that's the case, then there's certain problems where you can prove that memoryless things can't do well. In those cases, I don't know how to extend up to even 1 bit of memory. Often you can say, no matter how much randomness I use or something like that, even a random algorithm, so-called BLE random algorithms that use 1 bit of memory, 1 bit of randomization, they may not be memoryless because you may have to remember that bit to know what to do going forward. Okay, but if you're using fresh random bits, that could be a memoryless algorithm. But we just don't understand these things. We do understand for certain problems there's thresholds of how much randomness you need, but I'm saying this distinction about memory versus non-memory is we don't understand that. And we don't understand how restrictive is greediness, because the decisions. So I think that's it, and I really want to thank you again for inviting me. And I do want to follow up on what the director of the Institute said. These collaborations are really critical. I would love the opportunity to, misspelled opportunity, but I still mean it. I would love the opportunity to discuss any thoughts about online algorithms and how they relate to distributed computing or networks. So thank you very much again for inviting me, and I really hope I get a chance to talk with people and answer questions, but maybe I haven't left time for questions, I don't know. Whatever. Thank you.